Yes. It's about programs, proofs and refutations, and tests and mutants. Go ahead.
All right, thank you. So, yes, so I'm presenting this essay. Can you all see the paper? Can I hear you? Can you all see this? Hello?
Can you make it bigger? A little bit.
Yes. I
Perfect.
don't know exactly what it looks like on your end, so I just wanted to see if you can see the title and anything that I'm sharing
Yeah,
in the
that's
browser
good.
windows. Okay, so this talk is in the form of a dialogue. So I thought about how to present this, and at first I practiced actually reading the dialogue, and then I decided that I'm not Rich Little. I can't imitate enough different voices to make this not sound fairly ridiculous. And then I actually had in a class, I'm teaching a couple of software testing classes this semester, it turns out. And I had students actually read it out and thought that was entertaining and tried to recruit students to read it aloud. And we found out that the timing doesn't work and students are fairly reluctant to do this, I think, for reasons of embarrassment. Although a few were very game, I couldn't get enough together to make it actually work as sort of a skit, if you will. So then I thought, a talk should really be an advertisement for a paper and the research in it. And for an Onward essay, really, the research, there isn't in this a conventional research agenda. I'm not offering up a new, I think, scientific proposal here. I'm simply musing on certain ideas that are out there. So I thought the better thing to do would be to first start off by saying where this paper is coming from and what else you might even want to read more than this paper itself. I hope you'll read the paper. And second to, if it works in this remote setting, I actually, unfortunately, couldn't be there because I was sick the other week and sort of I'm catching up on some things that had to be done in time. But to open the floor in some sense to comments on these issues. So I'll probably do a little bit longer question session than usual. But I thought I'd first say, so this paper's title, which is a bit confusing and ugly, is a tribute to Lakatos's famous, I hope still, book, Proofs and Refutations. So this book is not about software engineering. It's not about programming languages. I think it has been highly inspirational to people involved in these things, especially interested in the question of how we know if a computer program is correct or faulty. I think the biggest differences are that Lakatos' book is much, much longer than the essay. It's 184 pages or so. And that its topic is polyhedra. And a set of students in a classroom talk for an unrealistic large number of pages. This is a very long dialogue over a very large number of days in class. And they talk about what the term polyhedra means. And they talk about what it means for a theorem about polyhedra to be correct, which turns out to be just as much about the question, what does the term polyhedra mean, as it does any particular theorem about what is true of polyhedra. So there's a negotiation between the definition of polyhedra and the things that are true about polyhedra. So I think this is why this has been so inspirational to computer people, in that in the end, whether a program is correct is a negotiation between what the program is and what the notion of what that program should do is. And I think there are a lot of questions about this that are really still poorly understood because they're just as difficult as in mathematics. So in Lakatos's book, polyhedra are pretty interesting. At the end of this, you're very interested in what it should mean to call something a polyhedra. And I think it's interesting that in computer science, you can actually, here is the artifact. It is the code for binary search. anyone who finds the definition of binary search as interesting, as complicated, as worth arguing about, I don't think I could spend 50 pages, much less 100, talking about what binary search means. So there's this question of, okay, so is our problem less interesting and less complex? But then if you think about the other side of it, polyhedra are only more interesting, easier to understand. I mean, more interesting, less easy to understand, easier to argue about than something that's essentially a toy. And if we considered real code, let's take popular library, pandas. What does pandas mean? Well, I think that what pandas is supposed to do and whether it's doing it is a question that, in a sense, is less interesting, but is vastly more intricate than the question of what polyhedra are. I think there's no one who, even if they devoted a lifetime to it, would actually for sure say that they have a very good understanding of what any really complex software artifact is supposed to do. Whereas I think even if you're arguing about the details of how we should define them, almost everyone who studies polyhedra very long will have a general idea of what they are and have some fairly well-informed specific opinions about what they are. So this dialogue is a short version that talks about the question of how we know if a program is correct. And we do that in the dialogue, and the suggestion of the dialogue is by a process that is a matter of proving, whether by test or by actual mathematical proof or by sheer force of will argument, that the program is correct, and then refuting that somehow. If our proof doesn't hold, in the case of test, the proof will refute itself, and going back and forth, negotiating this. And this ties to the famous essay, well, paper, although I think it's really more an essay than a paper, of DeMillo, Lipton, and Perlis, social and programs. And it is a dialogue, and it is a social process, but one of the things this paper wants to say is that the ideas of this as negotiable, as social, as hard to determine, as something involving human expertise, do not preclude highly automated approaches to determining how well you've specified a program. And so in particular, the core message of the dialogue, I think from a practical point of view, is an argument for the modern version of mutation testing. Because not so much because it's such a great improvement over, say, traditional code coverage, but because unlike code coverage, it gives us insight into the question of whether we've properly specified the program at hand. So before I dive into, I was going to go through the sketch of what the students actually talk about in case anyone wants to know but doesn't want to actually read this. But I thought before that I'd open up to any questions from the audience about anything you particularly like here. To hear about, to ask if you have an opinion on this general topic.
Any opinions at this point?
Okay.
Yeah, we have one.
If no one has...
Yeah, we have one.
Fine.
Just a second.
Oh, someone has something? Sure.
Hi. Yeah, I have an opinion. I just think this is really...
Yes, go ahead.
It's really fascinating to see the format for this. In our Onward essay, we also did a dialogue, but I think it was sort of coming at it from a different point of view. So I'm just really excited to see more. Well,
the dialogue format, actually, the most interesting thing to me was that during reviews, one reviewer, who I think may have been the author, and that's fine. I don't think there's anything terribly big leaking out here. Pointed to a dialogue, actually, that this dialogue references that's actually on very similar topics in a different venue some years ago. I don't know, people... Perhaps actually in my case, it just comes from... If you read the Lakatos work and you're thinking about it, which I was doing while writing a review of Donald McKenzie's paper on trust, basically, that covers modern correctness. I think you just feel inspired to write a dialogue. It's sort of like, I imagine that there's a million philosophy undergraduates who've read a few Platonic dialogues and sat down and written a dialogue about something as a result, just because you're so inspired to by that format and how interesting it can be. Now, I don't think mine's as interesting as Lakatos or anything, but yeah, I think it's an interesting format to write up these thoughts in, where you actually, I think Plato maybe had this key thing here. If you don't totally want to reach a conclusion, you just want to raise a lot of questions, a dialogue is a very good way to do that. Whereas a normal essay, you're at some point probably going to have to say what your opinion is more.
Yeah, thank you. That's good to hear. I just add that in our first draft, we sometimes sort of switched out of dialogue format, and some of the feedback we got was, no, stay in the dialogue format. This is we want to hear it more. So
well, I actually interjected a lot of author injections because the reviewers wanted a little more commentary from the author mixed in with the dialogue. So maybe we converged in some ways.
Yeah.
Did you end up with a pure dialogue?
Well, the thing is, in our dialogue, it's us having the dialogue. So, you know, the authors were
okay, it's the authors.
But I guess, like, it's not really the authors, because, you know,
it's artificial voices of the authors.
Yes.
Actually, I think it would be reasonable to call this paper perhaps a dialogue with the author. It's just that it's the voices in my head that don't all agree on what software correctness means, rather than actual individuals collaborating at all.
That's great. Thank you. Thanks for that insight. Thank you.
Sure. Anything else before we proceed?
I think you can proceed.
So, since I don't want to read this out loud, which ends up being very awkward, I will say the setting. So the dialogue, like Lakatos' book, which I strongly recommend you read. In fact, if you only pick one thing, my essay or Lakatos, read Lakatos. It's much more interesting and important. But the dialogue is in a classroom. And in the original, basically there's a theorem about polyhedra that's proposed. And then students end up arguing at great length about, is this theorem correct? Finding a polyhedra. And in this much shorter dialogue, what's happened is the class has looked at an implementation of binary search. And the professor has made a mistake in class in the original implementation. And I based this choice of binary search on a few things. So first of all, binary search seems to be the thing to talk about if you're going to sort of abstractly talk about proofs. So Hoare's famous first paper on Hoare logic uses binary search. John Bentley in Programming Pearls proves binary search correct. And then 30-some years later, I believe Joshua Block showed that actually the proof was wrong, and most binary searches are technically incorrect once you get to the point where you can have overflow in the arithmetic determining the midpoint. Which I thought was interesting, in that it is true that actually the proof carries. It's just that Bentley proved it in a world where, you know, C or whatever language, Java, has infinite precision arithmetic, and there's no overflow. But in practice, that's not actually the world we live in. It's actually easier to prove the code for infinite domains than it is for the actual sort of annoying finite domains we're dealing with as computer scientists. And the other reason that I thought of this was that the late John Reynolds, when I was taking a seminar in grad school with him, actually wrote up a binary search on the board and then said, now this is almost certainly wrong, because every time a professor writes binary search on the board, unless they're consulting something, they'll get some detail wrong. And that's why we need to prove programs correct, because even if we write binary search, we're actually going to get it wrong. And I will have to say that over the years, I've seen a number of students and professors write binary search up, and I don't think John Reynolds was 100% correct. I have seen people do it correctly, but it's certainly the case that 80% of those have been wrong in some way or other, even ignoring the midpoint computation. So the students after class So I got the teacher out of the way. Lakatos has his teacher around, but I didn't want the teacher in the way. Are talking about this code, and they end up coming up. One of the students was a fairly obnoxious computer science philosophy double major who basically says that everything is messed up here because even if we prove a binary search implementation correct, how do we know that our notion of what it means to be correct, our specification, is correct itself? And the students wander around this quite a bit and incidentally introduce a number of sort of interesting lesser-known methods of testing. But they sort of float mostly around this central question of how you know if the specification is correct. And that comes from the things that inspired me here, and that Lakatos' book, Proof and Refutation, I think is about how you know if the notion of the mathematical object you're proving things over is correct. Now, in math, this is a negotiation in a lot of ways between what you can prove, what kinds of theorems are interesting, and what definition of the objects makes some sense. Unlike in computer programs, the math, unless it's connected directly to, say, a problem in physics or something, often doesn't have the same limiting property of we have some use of that mathematics. You could probably define some reasonable objects as polyhedra that, you know, all will work about the same for the purposes people actually do anything practical with polyhedra. Whereas binary search, if your notion of binary search correctness drifts too far from it can find items in a sorted array, you're not really doing anything useful at that point. You might as well call it a day. There's nothing going on there. So computer science is more grounded here. We can't just have fun in the same way, at least if we're implementing real software, and no one ever tests academic software, so, you know, that's pretty much where this notion of test and proof is going to come in. There's the book, as I mentioned, by McKinsey, which is a sociological examination of these issues. It's called Mechanizing Proof, Computing, Risk, and Trust, and I really, again, recommend this book. I think this book is less fun and less deep than Proofs and Refutations, but as a history of the effort to make computer programs correct, I think it's a really excellent book. It does cover all of the viewpoints, I think, that you would want to look at. It talks about formal proof, model checking, core logic. It also talks a great deal about tests and practical approaches to this, and Dijkstra's arguments, and in some sense arguments with everyone over this. And it really focuses in on DeMillo, Lipton, and Perlis's social processes and proofs of theorems and programs. And all of these three works, actually, I think, social processes and proofs of theorems and programs, proofs and refutation, and mechanizing proofs, are the things that make this dialogue. In some sense, if you read those three books and came at it as a software testing researcher with an interest in background in formal specification and model checking, which I was originally in, and then a career mostly devoted to very practical testing, I think that's not too hard to arrive at this. Anyone else with that background could have come up with this if they decided to write a dialogue after reading these things and doing this. So, the students discuss this. There are a lot of problems with getting everything correct, and the students end up diverging into groups based on how ambitious they want to be. And so one group essentially says, yes, it's a social process. You'll never know your specifications are right. Formal proofs might be interesting. They might help you find bugs. But in the end, we have to sort of give up and trust people. And where I come down is that, yes, there is a great human element of imagination here, but that, and this is a bit of an argument with Dijkstra, the specification is not something that has to just be left to human intuition and ideas. You can have the computer help you with human intuition in that sense. And the proposal there, if you want to think of this as a white paper instead of just a think about it dialogue, is that That is really the reason mutation testing is interesting. If you introduce bugs into a program and your specification doesn't help you find them, that is a way to know that your specification isn't what it ought to be, because a good specification should rule out most programs except for ones that actually do the job. If your specification doesn't rule out enough things, it's not a very good specification. That's the fundamental method that some of the students at least go away excited about. And that's what I think is the way to get out of reducing this to people have to come up with good specifications. And the way to do that is to have lots of meetings and think really hard. I do think it's true that specifications that lead to tests, at least, or proofs, automated verification efforts of any kind, can be checked, because you can see if they rule out most of the programs that are similar to the program under test. And if they don't rule out enough programs, there's almost certainly something wrong with the specification. That's the practical side point, but it's not necessarily what the dialogue as a whole is about, because the students wander around, and I think, it doesn't solve the problem. There's still this human effort, and perhaps in sort of traditional Plato style, actually. At the end, Alpha notices this problem where you have the overflow issue. And I'm not convinced that Mutants would help you find that issue. I don't think you're going to produce a version of the program that exposes this bug, because you have to think in a larger context. So it's not as if you can get rid of the human effort. But I do think it can be more automated than, say, Dijkstra argued, where Dijkstra basically made this argument that the specification is not his business. You have a good specification is what you assume, and then your job is just to prove that the program satisfies it. The specification is not a mathematical thing, because it's something that comes from users or from whoever wanted the program written, and their job is to get it right, and if they don't, that's their, bad lookout. So that's a summary of what the essay says. So are there any questions about that? I thought I'd show the code that goes along with this also. Sort of make my argument that, at least for binary search, this works pretty well. So does anyone have any questions before I proceed to actually showing the stuff that accompanies? If you don't want to read the dialogue, you can run the code.
Any questions at this point? Have you modified the dialogue? Have you? So to which degree was the dialogue modified for the essay?
The dialogue, actually, the reviewers, I didn't end up modifying the dialogue per se a lot. What I mostly did was, if you look at the paper now, there's these sections where the students talk, where, as the paper says, let's listen in. And then we see the code on the whiteboard, and the students talk for quite a while. But then at some point, the author interjects, and there is commentary. That commentary was originally a long postscript, and I do think it actually improved it in that waiting until the very end to hear these comments and references and sort of stepping outside the dialogue, I think was a mistake. Lakatos is working at a lot longer length, so he can just, also he has the teacher around to sort of interject as the author to some extent. But without the teacher around, I think it was a good idea to move much of the postscript up into the dialogue. I think it reads better. And when I had actually a class go over this, they actually said that the comments helped them understand what was going on in ways that might have been fairly hard with just the dialogue. So I think it was actually, actually, when I've written Onward essays in the past, I've always found Onward essays have a really good review process that seems to really actually do a pretty good job of improving essays. Maybe all essays should be written there. Actually, probably most famous essays in history since at least, the 1900s have been written by someone negotiating with a good editor, if anyone remembers them. So Maybe that. Actually, probably Plato read aloud his dialogues to students, and they argued a bit, and they were improved. So, you know. You have students like Aristotle, that probably works pretty well.
So,
All right, so I'm going to switch windows.
just a quick follow-up. So
did
you
say
suggest
something?
to read the entire dialogue first and only on the second
I would
second
suggest reading. So actually, if you care about this topic, and you don't have time to sit down and read Lakatos and Mackenzie and all that and ignore me, I would suggest reading the essay, which is pretty self-contained. And then if you're interested in binary search and the kind of tooling this talks about, to do what I'm about to do and step through the code that accompanies the essay.
Okay.
Let me pull up. Okay, here we go. So, is this big enough to see? And are you guys seeing this yet?
Maybe a little bit more bigger.
Okay. It's not appearing for me at all, but you guys do see it?
It's a little bit
You see
small
a
in the
bash
back.
window?
Yeah, we see the bash. It's a little bit small in the back.
Okay,
but,
good,
yeah.
good. Because it's not appearing for me in the Discord. Okay, so the steps to get this running are do a Docker pull, which this machine should have already done, but
Can you
it may
increase
be
the font
checking.
size
Yes,
a little
it's
bit
up
more?
to date. And then
Sorry, can you increase the font size?
make it a little larger.
Yeah, yeah.
Is this large enough?
A little bit
Can
more.
you see it better? A little bit more?
It's like,
More? Tell me when.
well,
Is
it
this big enough?
doesn't do much. Just the window's getting wider. So like, can you increase like double the font size or something?
I'm not sure it shall. All right, let's look if there's a setting here. Shell. Oh, I see the background color. Window. I'm looking if there's a setting for the font. Well, default font size, I think, is going to be bigger. Did that help? Is this helping?
It didn't change.
It didn't change? That's interesting. Because I'm actually telling it to make the font bigger, and it's getting bigger in my screen. But apparently, I have an idea. Hold on. The font is bigger. I think if I shrink the window. Did that help?
Maybe go halfway back. Yeah,
Halfway
something
back.
happens. Yeah,
This?
a little bit more. Okay, keep
Little
it
bit
that
more.
way.
There?
Stop.
Did that work?
Yeah, yeah.
Okay. All right, so we'll run the Docker container, and now go to Onward code. Okay, so in this directory, there is the infamous binary search implementation that the students argue about. And there is a lot of code to actually test this. So, and because I'm talking about mutants, I'm going to say that the first thing to do is to mutate that file and come up with all the variants of binary search. So these are what we're going to use to see if we're specifying binary search well enough. So it's going to run through the lines of code and throw out anything that doesn't compile. And we'll end up with 85 different variations of binary search, 47 that don't compile. And then this would be if there were some that are semantically equivalent, but we don't have a way to check that for C. That works. So now we have this directory that contains 85 versions of binary search. So if we want to look at the kinds of things that this does, we diff bin search.c and mutants bin search. Oh, it's 45. So we've changed if the middle value is less than the key to if 1 equals 1, which is just an if true. So that should break binary search, right? I'm thinking it's probably important that we compare the middle value to the key. All right, so we do a make and test bin search. This runs a test using a tool called Deep State that works like this. So it includes the binary search code. It picks a size of the array up to some max size. I chose 32. So we're not going to find the overflow error here. It picks a random target and decides if that target's going to be present or not. Populates the array, sorts it, because binary search, one easy mistake to make in testing binary search that if you do it in class for students, you'll forget half the time, is that you do need to sort the array you're generating. And then if we decided to make the element present, we assign that target to be something that's in there. And then we just check that the binary search result is correct in the sense that if binary search returns the item is there, it better be. Otherwise, the item better not be present. So this is generating test data and then running it. Now, if you just run test bin search, that it'll generate one test, and that test will have size equals 1, and the array will just contain 0. It's not a very interesting test. But the deep state harness lets you run pure random testing. So we'll do 30 seconds of random testing here. And it'll tell you that it ran 327,000 tests, and they all passed. So that would actually give you a reasonable amount of confidence. I think binary search is a program that a few 100,000 random tests will probably find most. So you can also use the AFL++ fuzzer to generate test data, which is, I think, a bit of overkill for a binary search, but will also, in 30 seconds of AFL testing, you'll be fairly confident that your binary search is correct, because you'll cover a lot more interesting ground than you will with pure random testing. So this is all just running various kinds of tests. So the mutants will let us find out if we actually catch all the variants of binary search with this. So the command to do that, analyze mutants, you give it the source file, binarysearch.c, and then how to run the test. So make clean, make the test, run 15 seconds of pure random testing, immediately stopping if you find a bug. Give that whole process a timeout of 20 seconds, and then the mutants have already been generated, and they're in a directory called Mutants. And if we run this, it'll show us mutants, and it will tell us as it. So if we go down here, the first two mutants, it almost immediately detects in less than a second of random test generation. And this mutant takes a while to kill because it introduces an infinite loop, as you can see. So if the midpoint is not the low plus the high divided by 2, but the low modulo the high, the midpoint can actually hit inputs where it just loops and loops on the same thing. So there's 85 of these. It's running through them. It's going to take a few seconds for a number of them. But in the end, we'll end up with a pretty high mutation score. Binary search turns out not to be incredibly hard to define well if we, just check that it actually is reporting if the item is there or if it's not and it has the correct location. So if there was something wrong with our specification, our mutation score would be a lot worse. So the way to play around with this, if you want to convince yourself that this is useful, is to take that binary search test harness and just change it to miss certain modes of bug in binary search. So one thing to do is to not check for the case where binary search detects that the item isn't there. Have it always be in the array and then run and see, and you'll find out that indeed you miss a lot of mutants. They only cause problems in the case where the element isn't there. So you really do end up with mutants with a good way to just see what's wrong with the program. And the mutants, the students talk about writing what they call a buginator because they've never heard of mutation testing. And, they're going to go off and think at the end, students, about how to do this. So mutation testing over the years has just developed to be coming up with a number of really sort of fairly common sense things to do to a program. The kinds of things we're seeing go by here, modifications of arithmetic operations, deleting statements and such, and just trying those out. And I think this is a pretty good answer to these deep questions in some ways of how do we know if a specification is good? My answer would be, well, to really know is very hard. But one easy way to know in most practical contexts of programs we want to test or prove correct is simply to inject a lot of bugs in a sort of unbiased way and then just see if we can find those bugs. That's the practical upshot, which is really just a, salesman's pitch for mutation testing. But I think mutation testing is often viewed as just something better than code coverage, whereas I think it's quite different than code coverage in that code coverage can't really tell you anything about your specification. I think most of the interesting things mutation testing tells you are about your specification. It can tell you other things as a kind of proxy for code coverage, but what it tells you that no form of code coverage could tell you, unless you consider it a form of code coverage, is about if you introduce a bug, is your specification good enough to notice that there's a bug? And that, I think, connects to this bigger picture of, say, the mathematical question of, is a theorem true in a way than code coverage does? And I think we should probably be using this more often now because we finally have the computing resources. It's not too expensive to do it. And those of you who are at all into the testing community probably know a number of big industrial developers. Google, for instance, quite recently really started pushing mutation testing. Actually, a colleague of mine, author on some other papers on mutation testing, Claire Legou at Carnegie Mellon, her husband is a developer at Google, and I don't recall the exact wording, but Claire was telling me, he was noticing that Google was now making new check-ins go through some mutation testing and said, this is going to be annoying. It's not that useful. And a few weeks later, he said, hey, that was really useful. It found, things that our tests were missing. So I think this is something that, once upon a time was sort of viewed as an impractical academic approach to testing and that I think probably is useful in the real world, but also has the benefit that it actually brings these deep issues of, is your spec good enough? Not just are your tests high quality, out in a really practical way. And I think that really what it's doing is something like what the students in Lakatos' dialogue are doing, in that they're sitting there talking and coming up with ways in which the current definition isn't actually good enough to catch holes they're trying to poke in it. Mutation testing is just getting the computer to poke holes for you. And I think we're about up with time, so I should probably open to questions.
Thank you again for the demo and talk.
Sure.
Well, I've got a first question about the students behind the dialogue. How high is the level of frustration in these discussions about, because also of this, loose definitions, uncertainty, is this the right specification, right? So this kind of...
I actually, this semester, had an undergraduate and a graduate class, because I happen to be teaching 2 testing classes this semester. Go through basically not quite the same dialogue. The students are not as well coached and wander over the place more. But the question of coming up with a good specification for binary search, and I think probably the students in the dialogue are more troubled than real students, in that real students probably have a lot more focus on actually just getting the job done and getting a working binary search. So actual real students are a little bit more focused on the task and did a quicker job of coming up with a good specification than the imaginary students.
Are there questions online?
But I think that's because it's binary search. I think if it were a more complicated program where the question of what it should be doing is harder, people in real life are a lot less focused than these students, even if they're experts, just because for real large programs, figuring out what the program should do is so hard to start with. But if we have any notion of it, and we've got to the point of practically testing it, fake bugs are still a pretty good way to find out if we know what we're doing.
So there are no questions.
A lot of this really comes back to, you're in Pasadena, and I wish I actually could have been there and hadn't been sick last week and sort of caught up with some other stuff. But I worked in Pasadena for several years at the Jet Propulsion Lab, and actually one of my great frustrations working on tests as part of the Laboratory for Reliable Software for the Curiosity rover file system was we really didn't at that time have very good mutation tools that were practically useful for real C code. There were some academic programs, but they were hard to run. They didn't always work well on, a modern Linux machine. And actually, I think it would have helped us find more problems quicker if we'd had that available.
Okay, then let's thank the speaker again.
All right.
If you have more questions, use the Discord channel. And yes.
Okay.
Thank you.
All right. Thank you.